So I think we have quorum because we have about 13 people. So let's get started. It is my pleasure to introduce Dr. Baptiste Royer. He did his PhD in theoretical quantum computing with Alexander Blaise at Sherbrooke. Then he went on to work for about 3 years in the group of Steve Girvin in Yale. And since about a year, he came back to Sherbrooke for a faculty position where he leads his own theory group at the moment, and he's going to talk to us about encoding qubits in oscillators. We're looking forward to it. Take it away, Baptiste.
Yeah, you can see my screen all right?
Yes.
So yeah, thanks, David, for the introduction. So I said I'm a theorist, and these are results obtained at Yale, but I'm going to present a lot of experimental results obtained in the group of Michel. So yeah, to start with, I'll just start with the acknowledgement that the experimental results were not done by me, so mostly the work of Vlad Sivak here and Alex Eichsbusch in the group of Michel Doré. So yeah, this could not have happened without them, and also the work of my theory collaborators, so Shraddha Singh and of course my supervisor Steve Girvin. And so, okay, in this work, we were interested with the question, like, okay, can we perform reliable quantum computation with imperfect qubits? We know that if we want to build a quantum computer, we'll not need a lot of qubits, and these qubits are imperfect. And if we don't do anything special, then for sure we'll be overwhelmed by errors. If we have many qubits, the probability that we have errors go up, and yeah. And so the solution is to do quantum error correction. However, all of you might know that quantum error correction is very hard. And so here I just want to flash a picture from the experiment done by Sebastian Quiner at the group of Andreas Waraf at ETH Zurich. And the only thing I want to convey in this slide is that correcting errors is hard. So this is an experiment of a repeated error correction for a surface code of distance 3. And it's a huge chip. There are many qubits, many cables, and so many things can go wrong when you do this. And also you need to do a big circuit, and in principle you can correct one error, but only one error. And so there are many gates, so that increases the probability of error. And so you can really ask, is it really useful to do all of this? Can you make it useful to have error correction? And here in this work, we think we're the first ones to show really that we can get a lifetime improvement of the logical information by a factor of 2. And so what exactly do we show? Yeah, so feel free to interrupt me if you have questions during the talk. And so what exactly did we show? So maybe I can talk about what people usually compare in quantum error correction experiments, because we're not the one to do quantum error correction experiments. So one thing you can look at if you have a big circuit is what's the best physical element, what's your best transmon in this case. And you could use that to do your quantum computation. Then the second thing you can do is you encode your logical qubit in many qubits, but not do any error correction. And so for sure that will be worse than doing your best physical element, because you have more qubits, so there'll be more errors. And then you encode your qubit and you do all your error correction, and the hope is that things got better when you do this. So a lot of time in quantum error correction paper, people compare the encoded qubit plus error correction to the encoded qubit. And so that's the first level, showing that you're actually doing something with your error correction. But ideally, you're doing something useful, and your lifetime is better than what the element, the best element you started with. And here in this work, that's what we show. We show that we can improve on this best physical lifetime by a metric I'll precise a bit later, by a factor of 2.3. And how do we do this? We replace all the physical qubits, the ensemble of physical qubits, by just a single microwave cavity. So we encode the information redundantly, not in many qubits, but in a single element with a larger Hilbert space. And instead of having many auxiliary qubits to do the measurements, we only use one. And with this, we can show that we can improve the lifetime of the information. And eventually, to build a quantum computer, our argument is that, well, the hardware overhead for this architecture is not too much. And so with a minimal hardware overhead, you can hopefully gain a large lifetime improvement. And so that can help build a quantum computer. So comparing against other repeated error correction experiments, there are many. So I just want to highlight a few ones. So first of all, we have to acknowledge the first hero experiment by the Yale group in 2016, where they showed an improvement slightly above 1 of 1.1, I think. And the problem in the experiment is that the qubit was not infinitely long-lived. It was a cat state that shrank back to the vacuum, and at some point, you lose your qubit in this scheme. And so here we have a nice improvement, and it was also the work in the group of Lujansen, who I think appeared the day before us on arXiv, or 2 days, I don't remember. Anyway, so according to this metric, we did pretty well. According to this metric, we came up. And so, okay, I want to start discussing a bit the experiment and start with discussing what's the device a bit more in a bit more details. And so we used a single post cavity. So it's a block of element that's been drilled where you have an electromagnetic mode here in the middle. And so in this memory, its characteristics are here. And it was a pretty good lifetime, but it was not the best lifetime that have been demonstrated in the community as well. The second thing here is coupled to an auxiliary transmon with a fairly decent T1 and T2, which was due to the change in fabrication technique they used to tantalum to build a transmon. And as a theorist, I had absolutely nothing to do with this improvement. But I want to highlight here one unusual thing in this regime of circuit QED. So we work in the dispersive regime of circuit QED. But I want to point out here the numbers. So the dispersive shift is pretty small compared to standard experiments, either in bosonic codes or for readout resonators. I think it's more it's more common to have chi's of the order of megahertz. And we want to have a low chi because we want a low nonlinearity, which is here very, very low. So we want to use the whole Hilbert space of the harmonic oscillator. And so we want the oscillator to be as harmonic as we can. And for that, we reduce the chi to reduce the induced nonlinearity to a very low level. And then here we have a readout resonator used for readout of the transmon incident. So what we'll do is we encode the information in the bosonic mode, and we use the auxiliary transmon for quantum control. So now what's the code that we use? So for those who have seen this before, I apologize, but we have to present what's this, the GKP grid code. So introduced by Gottesman, Kitaev, and Preskill more than 20 years ago now. And the idea is the following. I like to think of it that way, that we want to encode a qubit in a harmonic oscillator. We can represent a harmonic state in phase space. And so one way to represent the problem of encoding, how to choose a code, is how to place a real estate problem in phase space. So we have two states, 0 and 1, and we want to choose where to put it in phase space. And to have as much redundancy as possible, one option is just to tile phase space and say that your zero radical now is a superposition of all the blue rectangles, and 1 is the superposition of all the red rectangles. And so how do we describe this state? Well, the best way to describe this state now is as a lattice. And what's a lattice is just a system that is invariant by translation. Here, translation by something that has an area of 4 pi to place twice this area. And so the best way to describe the state is a state that is invariant by shifts in 2 square root of pi in both position and momentum. In general, translation in phase space do not commute because they are a non-commuting variable, except in the special cases where you look at translation that cover an area of a multiple of 2π, which is the case here. So we can find eigenstates of both these. So maybe this is a bit unwavy, so maybe we can look, yeah, so we can do also logical operations. Maybe you can guess that the logical bit flip here is just a displacement by alpha lattice constant, which maps blue to red and red to blue. And we can compute with some math that is a displacement in the other direction. And in this talk, I'll be mostly focusing on memory, so I'll talk minimally about gates. So what do the wave functions look like? To think about this, you can look at these two translation operators. We know that translations in momentum are generated by position. And so eigenstates of that operator will be eigenstates of position. And if we want the +1 eigenspace, then it will be all the position eigenstates at multiples of square root of pi. And so in phase space, we represented them by infinitely squeezed state, so vertical states at all multiples of square root of pi. Same thing, translation in position is generated by momentum, and so same story, eigenstates will be multiple of square root of pi, but in a momentum. And now if I want the common eigenspace of these two, so I want to be invariant by these two translations at the same time, then I take the intersections of these states. So it turns out that the project 2 into the code space gives you a grid in phase space. And so these codes are often called grid codes for that reason. And yeah, so if I write the code words, then the 0 logical, I can call it, it will be a superposition of all even multiple of square root of pi, and 1 will be all multiple of square root of pi. And you can check indeed that they respect both these, they are +1 eigenstates of both these translations. So up until now, I've described what we call the ideal code words, and they're ideal because the map works out nicely. The problem is that they're not physical because they constituted of infinity squeeze states. So they extend infinitely phase space. They're not normalizable, infinite energy. So that's bad. So instead, what we usually do is we consider the finite energy GKP code, where we take these ideal and we apply Gaussian envelope on this. Which is, yeah, applying Gaussian envelope in phase space. And this has the effect of broadening each peak. Instead of having an infinitely sharp peak, we have a small Gaussian whose width is inversely proportional to the width of the big envelope. And for mostly the intuition from ideal codes carries over from the finite energy code. So I've described what is the code, what are the code words. So I haven't explained why it's a good idea to do this or how to do error correction. So that's what I'm going to do now. So the idea is this code can protect against any small displacement. And why would that be useful is that for any small channel, for any operation that's applied on your oscillator for a small amount of time, you can expand it as a sum of or superposition or mixture of forces applied on your oscillator. And forces causes displacement, and so any channel can be expanded as a superposition of mixture of displacements applied on your oscillator. And if your channel is applied for a small enough amount of time, that these are small displacement. And this code can exactly correct for all small displacement that are inside the unit cell of the lattice. It works that way. Say you have some displacement like this. To do error correction, what you do is you measure the position within the bin, and then you just apply the reverse to snap back the grid into place. So in this case, you can exactly correct. And so this code can correct for photon loss, Kerr, oscillator dephasing. It's not super great to correct against Kerr and oscillator dephasing, but numerical studies have shown that it's the ideal code to protect against photon loss. Which is surprising because that's not what it was built for, but it turns out that way. So if you have large errors, large displacement, for example, here you get a large displacement error, then you measure the position within the bin, but what you'll measure now is this position. So you apply a correction to map this point back to the origin, but you've shifted the grid by one lattice constant. And if you follow also the image here, you see that now you've created a logical error. And so that's bad. So as long as your error channel can be expanded in terms of errors small enough, then this code is very good. The question is, how do you measure that thing in practice? And so we can look back a bit. What is this operator? So transition is momentum is generated by position. And we want to measure the stabilizer. And so we want to measure this. And so measuring this, it's an complex exponential, which maps back to itself once x you've displaced by square root of pi. And so this is equivalent to measuring the position modulo square root of pi. But if you look at this, we have algorithms to measure that, and that's called the quantum phase estimation algorithm. And so to do error correction, we just do a variation on the phase estimation algorithm. And so here, for example, is the 1-bit phase estimation algorithm in this case, where you prepare a qubit in the plus state, so G plus E. Then you apply the control translation. Due to the phase kickback, your qubit will end up somewhere on the block sphere, and then you measure along the y-axis. And then you can measure if you displace a bit on the right or on the left. And so with this, you can measure 1 bit of the phase, and then you apply a little correction depending on what you measure. And it turns out that measuring 1 bit at a time is enough to get a good error correction. And so I'll show the actual protocol in the next slide, but it's just a variation of phase estimation, and we measure 1 bit at a time, we correct, and that's how we can correct errors. And so the actual protocol is this one. So we start a qubit in plus, we have this series of control translations. So this middle part is the phase estimation part that maps the information from the oscillator to the qubit. We have the error correction part, which here we choose to make autonomous. So instead of measuring and then applying a conditional operation, an operation condition or measurement result, we apply the conditional operation, which, if there's no error, is completely equivalent. And then there's this finite energy adjustment part. So one problem if you don't have this part is that you do phase estimation, so you measure the position modulo. But if you repeat that, then you'll tend to project in what the basis in which you measure, which is position. And this basis has eigenstate infinitely squeezed state, and we know that if we try to do highly squeezed states in practice, it will fail. And so we adjust a bit the protocol to directly target the finite energy code. If you want more detail about how this works, please ask a question I can go into. But it turns out that, okay, so this can correct errors in position. So for one stabilizer, we just do the same for the other direction, and then we repeat. And so the error correction procedure is just repeating that for a long time. In this also, this is fully autonomous. But in the experiment, we also measured the qubit, and it turns out that there's also useful information in the qubit. But the error correction happens autonomously in the protocol. And yeah, so that was the code. Before showing results, I just want to flash one element that was very important in that experiment, is that and that was reinforcement learning. So that's another work spearheaded by my colleague Vlad Sivak, where we ask how to optimize things in practice for an experiment. And especially we implemented an optimization algorithm for all our parameters that do not depend on any model. So the optimization happens directly in the fridge and relies only on qubit measurement results. The way it works is that we have an agent that sends some policy, some control parameters to the fridge. it evolved for some time. We see how well we protected the information at the end, and we just measure one bit, is did we have an error or not? And then we feed back this back to the agent, which allows us to have a loop where we optimize parameters. And this allows us to optimize some non-trivial parameters. For example, to do this control translation, we have, there's some pump with some strength inside, so some photon number. And it's not obvious like how hard we should pump to do that operation. And so there's a trade-off between going fast and then things start to break because of hard pumps, or we go slow, but then we get hit by T1, T2, and all sorts of decoherence. And our initial guess for what was optimal was not good, and the agent consistently learned to make us go slower. And so reduce the pump, yeah, turns out it was better. So I can go on to the main results of what we got. So here an example is a few snapshots of Wigner function of the cavity as a function of time. And so we start by initializing the state in the code space. So for that, we could have used the stabilization and the error correction procedure, but it's just faster to get some optimal control. We optimize some sequence of pulse that we give to the qubit that prepares, in this case, the -x state on the block sphere. But you see that it prepares the state, but it's a bit distorted. It looks a bit wobbly everywhere. And so we turn on the error correction. And then after 4 steps, we still can recover all the information. It looks very much the same like of this one, but all the distortions have been washed away. And now we have a nice grid, or at least as nice a grid that we can get in experiment. Then at 12 rounds, it hasn't moved a lot. So we really protect the information. And then if we look at longer and longer time, then eventually the interference peaks here disappear. But we still keep the grid. So the fact that we have the grid here tells us that we're still in the code space. But we're in a logical mixed state in the code space. So we are fully mixed state of in the plus and x basis, so plus x and minus x. Now if we quantify a bit this decay, so we can compare now the 3 main elements in our system. So we could have encoded the information in the transmon, and in this case, the transmon had a T1 of 290 and a T2 of 240 microsecond. Now, if we don't do error correction, the best thing we could have done is encode the qubit in the Fock 0 and 1 state of the cavity. So these are the longest lived states in our physical system. And there was a T1 of 610 microsecond and a T2 just below 950 microsecond. So now our main result is that if we encode our GKP, we perform error correction, then we get a logical lifetime for the Z and X logical lifetime of 2.2 milliseconds and a state for the Y logical state of 1.3 milliseconds, which is clearly much above what you got for the cavity. Here, the full dots are the error correction, and the open dots are the lifetime of the GKP code words without any correction. So it's below both the full dots and the state of the qubit, because the GKP code states have many photons. In this case, an average of 5 photons in each code word. And so to compare these different elements, we use the average gate fidelity. So we compare our gate, which is a memory. So here our gate is just identity. And we compare what we did to the identity gate. In general, as a function of time, the fidelity will not follow a single exponential. But if you look at small times, which is what we're interested in anyway, because eventually we want to look at low error system with lower errors, we can always do a Taylor series, so a short time expansion, and we get an effective decay rate. And in the end, it's just the average of decay rate of the X, Y, and Z. You can get this by average of X, Y, and Z Pauli eigenstates. And yeah, so now if we compare the rate of the best physical element to our best our GKP error correction, we our maximum that we could obtain was a gain of 2.3. Yes. So that's a very nice result. I just want to make a few caveats to make sure that I'm not claiming things that I don't want to claim. So here, this is really for the memory, and we haven't said anything about gates. And so a common objection is that, yeah, okay, you increase the lifetime of your qubit, but most likely you also increase the time it takes to do gates. And that's true. However, I don't think here in this case, the correct metric is, yeah, so a common metric to compare again is lifetime, but over T gate, so T gate over T logical. But here, I don't think that's the correct metric because we have error correction. And so even if the gate time increases a little bit, we can correct for errors in the gate. So I think we should compare not to T gate to T lifetime, but T gate to T lifetime to some power. And we're still understanding exactly how the error correction works and what errors affect what and how things affect. So I don't know exactly what is this exponent, but I think even if we increase the gate time, particularly the C0 time, I still think we can win with this system, but this has not been shown. Nobody has done a C0 gate for the GKP qubit at the moment. The other thing I want to point out is that you see here that even at 0 time, the fidelity is not 1, and that's because our measurement fidelity is not great. So that's another thing we need to improve on, is we need to improve our measurement fidelity. We have a few ideas for this. In this paper, we chose to focus really on the memory part. There was already a lot of things to figure out. Yes. And yes. And so with this, I think I want to move on to the second part of my talk, unless there are questions on this. Okay, so I can move on to the second part of my talk, is the multi-mode GKP code. So what are the next steps for this? And so if we want this to be useful for a quantum computer, then we have to imagine to concatenate this GKP code with some other qubit code, be it surface code or your favorite qubit code. And so now in each location of the surface code, instead of having a transmon or a fluxonium or whatever, we would have a cavity with a GKP encoding. And the idea now is that if with your improved lifetime, then you reduce the overhead that you need. You reduce the number of qubits that you need to do error correction. And so 2.3 is not enough. We need to do much more, but we're confident that we can improve on these numbers. However, one problem, that's a recurring problem for bosonic codes, is that, well, you notice that we need a transmon ancilla to do quantum control of the cavity. In practice, there are ways that an error to the ancilla propagates to the code. And so in the end, instead of having a nice lifetime of your GKP that you computed numerically to be very high, then you're limited by some fraction of the lifetime of the ancilla. So each time you get entangled with your ancilla, then you get susceptible to T1 errors. And so with the current architecture, we don't really win in the end, because you did pay a hardware cost to add your cavity and everything, but the lifetime you gain was not that much. And so that's the next big challenge that we need to solve. The first way to solve this challenge is to have an ancilla with a biased noise channel. So here, the nice thing with this protocol is that you're really limited by T1 of the ancilla. You're super robust to T2 of the ancilla. If you do the analysis, T2 phase errors only propagate as correctable errors. And so one option would be to use, for example, a heavy fluxonium with a very long T1 and short T2 to do quantum control of your bosonic code. That's one option, or for example, a Kerr-cat or a dissipative cat state. Here I want to discuss a complementary approach. Is to, instead of using a single mode GKP, what I want to convince you is that you can use two mode GKP. So we encode the GKP in two cavities, and this is more robust. This will be more robust than a single cavity. And so in the rest of the talk, I'll briefly introduce what I mean and how to define these multi-mode GKP codes, and give you some sense of how we think this can be better. So coming back now to the single mode, I want to maybe put a more formal way to define the GKP code space, and this is a way now that will be much easier to it will be much easier to generalize. So one way to see the GKP code space is that you take a lattice in R2. So in what I showed, we started with the square lattice, and you take each generator vector of this lattice, and you just say that your stabilizers of your code are translation by that vector. And then to make sure that it's a valid quantum code, that your stabilizers commute and you really encode a qubit, there are a bunch of conditions. If you're not familiar with this notation, it's suffice it to say that there are some math conditions. And so how do we build now a GKP code in multiple modes? Well, we do the same thing, just in higher dimension. So if you have a single mode, we have two quadrature coordinates, x and p. If we have m modes, where we have twice the number of coordinates. So if we have two modes, we have 4 quadrature coordinates, x1, x2, p1, and p2. And so we can follow the same procedure. We find a nice lattice in 4 dimensions. So now it becomes a bit hard to illustrate. But the procedure is the same. For each of those generator vector, we associate a translation in phase space. Now that can involve both modes at the same time. And these are stabilizers. So we define our code space to be +1 eigenspace of these translations. And now you have the generalization of the condition, which you need your stabilizers to commute pairwise, and you need to have the right volume of your unit cell to really encode a qubit. In particular, one nice code we found in 2 modes was the direct analog of the square code. Is like 4-dimensional cubic code, which we call the tesseract code because it sounds fancy. And so here, for example, the generators of the square code in the square root of 2 pi units are this way. So one along x, the other along p. And then if I wrote now the 4 generators, because there are 4 dimensions, you can write this way, where here this is the phase space of the first mode, and this will be the phase space of the second mode. So here there will be 2 generators, which you need displacements in both modes. Yes. So how could you, what's one way we could do this? Well, it turns out that the stabilization protocol is exactly the same. You just replace single mode displacements by 2 mode displacements. And so written this way, the generalization is immediate. And that's the work spearheaded by my colleague Alex Bush. Found a nice way to have to generate these control translation in the single mode. And we think that this technique is directly generalizable to multiple modes. And yeah, the idea is that you use the standard dispersive coupling, and you displace far away in phase space. And if you displace far away in phase space, then you'll get a rotation of the cavity that depends on your qubit state in one or the other direction. But if you look closely here, this direction, rotation here or here, roughly looks like a displacement. And with suitable echo pulses, you can really make that into a conditional displacement. So one thing that's nice here is that you don't need the chi to the 2 cavities to be matched. They could be different because then the interaction strength is adjusted by how much you displace in both cavity. And here I show an example of a cartoon where this could be in the Wyman geometry with two cavities like this, but what you need is two mode and an ancilla coupled to the two modes at the same time. So that could be two frequency mode of a single cavity, or two cavities, or any two modes. And they don't need to be the same frequency. In fact, it's better if they're not the same frequency. Yeah. And so, yes, with the 5 minutes that's left, I'll try to show intuition of why this could be better. So the problem with the single mode is that, as I said, errors propagate from the auxiliary qubit to the logical mode. And so I want to show a bit more intuition of how this happens. So in particular, in all their stabilization, there were some control translations in the code. So what happens when there's an error? The worst thing that can happen is an error during that operation. So if that happens, if you do the operation correctly, then if the qubit is in G, nothing happens. If the qubit is in E, you displace by the amount that you wanted. The problem is that if an error happens during, then you start displacing, then your qubit decays to G. So then you would lose the superposition between these two. E goes to G. And since you're in G, you don't displace anymore. You stop displacing. So in the end, you end up with a displacement error along that line. And so if you look at what error you can cause, then if you end up in the middle, that amounts to a logical X operation. And that's bad because there's no way you can correct it. And so for the single mode code, there's nothing there's nothing you can do against this type of error except increasing T1. For multiple codes, now you have a lattice, but in more dimensions. You have more dimensions to play with. And so here I'm giving a toy example. So again, for 4D, it's difficult to illustrate. So the best way I found to explain it is with the 3D lattice, but yeah, it's not the code, but probably all familiar with the cubic lattice. And if you take the face-centered cubic lattice, you can associate, for example, logical operations to this. And you see that in this case, if I apply twice X translation, I come back to a purple points, and my purple points are my displacement by stabilizers. And so here you get that twice displacement always give you identity in the code space, the stabilizer. And they also respect that X plus Z equal Y. So yeah. So we have different representative for Pauli operators, which is common for error correction codes. You always have multiple representatives for all your operators. But the nice thing here is that your stabilizers are not aligned with your Pauli operators. So if you get an error when you do this controlled stabilizer, then you fall somewhere on this line and it's not aligned with the logical operation. So it's much more robust against this type of error. And that's what we've computed. So we did numerical simulations, and and we computed that we could at least get a 6-time increase of robustness against ancilla decay errors. And moreover, we've calculated that this should get better as you increase the GKP size. For single mode GKP, secret mode GKP, if you take a larger envelope, it doesn't change your robustness against qubit errors, and so you don't gain. Here in this case, we think we can gain, and so we think we could get even better, but simulations get challenging, so that's why I'm not sure. And so to come back, we think that with an architecture where you encode the GKP in 2 modes at the same time, and then each of those is concatenated into surface code or whatever is your favorite code, then this could be a viable architecture for quantum computing. And with that, I'll conclude. Thank you for your attention, and yeah, I'll take any questions if you have some.
Thank you very much for the talk. It was really great. I enjoyed it a lot. So I find the idea of like integrating these GKP qubits into something like a surface code really interesting. And I was wondering if you could comment on if you expect using this multi-mode architecture where you're actually encoding the qubit in multiple cavities, if that might actually make the 2-qubit gates more difficult, or if you think that the trade-off there won't be too bad, because you did comment earlier on how sort of the difficulty of integrating a bosonic qubit in something like the lattice for a service code is entangling the GKP qubits.
Yeah. Yeah, thanks for the question. So it turns out that for the Tesseract code, the CZ gate requires the exact same elements. You just need the interaction time to be square root of 2 longer. So the gate is a bit longer, but it uses the exact same element, and you don't need to couple. You only have to couple the 2 cavities. So you don't need to couple 2 by 2. You only need to couple 2 of them. I'm not sure if that's clear. So in a sense,
yeah, I think I know what you mean.
Yeah, so it's I have exactly the same elements. So we think that the trade-off is worth it, but that's something we're exploring at the moment. Yeah.
Great, thank you.
Okay. Yeah. Other questions, comments? Okay, if there's not any more questions, let's thank Baptiste again. It was a very interesting and cool talk. Thank you.
Thank you.